Okay, we are told that we can proceed, and our second half of today's afternoon is about BEAMS, Accelerator R&D and Future Facility. So we present Accelerator Frontier Vision, and the talk is prepared by Steven Gourlet, Thor Robinheimer, and me, Vladimir Shiltsev. So we are conveners of the SNOMAS Accelerator Frontier. So we'll briefly go through, for general audience, we'll briefly go through what accelerators are, so you understand the complexities of the world we live in. Then we go through impressive progress we had since previous P5, 2014 P5. And then the bulk of the report will be in part 3 and 4, where we talk about our view of high energy physics, particularly accelerators for neutrinos, accelerators for rare processes, colliders, and 10 slides on our final messages, so we call them asks. Okay, let's start with accelerators. So accelerators already kind of approaching centennial. So the modern accelerators started approximately at the end of 1920s, early 1930s, when Cockcroft and Walton, Lawrence and Van der Graaf invented the first sort of modern or pre-modern accelerators. Since that time, accelerators and development of accelerators was awarded by 4 Nobel Prizes. Nobel Prizes just for development of new acceleration techniques. But of course, as we understand, accelerators are important for much more than ourselves. So approximately 1/3 of all physics Nobel Prizes were based on research carried out at accelerators. And that's only for physics. Many more Nobel Prizes in biology, chemistry came from the research carried out at accelerators as well. At present, there are approximately 140 accelerators which are used for research. Of course, the total number of accelerators in the world counts in like 30,000 to 40,000, but they're mostly industrial, small scale. Large research facilities based on accelerators are numerous. And be aware that we have approximately 4,500 experts working, running, and designing, and constructing these facilities, and about 15,000 of technical staff helping us to make all that happen. And altogether, we, as a world community, serve approximately 80,000 users. And of course, it's not only high energy physics, but also condensed matter scientists, biologists, nuclear physics, etc., etc. Approximately 1/4 of that workforce, quarter of the expertise, and quarter of users is in the United States. And we always pushing the envelope because the demands of our user base push us to invent new approaches to go to high energies, deliver better performance in terms of beam power, luminosity, brilliance, species of various kinds, all kinds of particles, cost, complexity, size, and R&D required. All that grows and grows and grows. So we are almost on the frontier. So the most advanced technologically accelerators are known to be colliders. They are relatively young, although it's already 60 years approximately young. When they started at energy range approximately 1 GeV or less. So this logarithmic scale in GeVs. So 1 GeV, this is 10,000 GeV. And over approximately 50, 60 years, the energies of these colliders greatly progressed. So particularly for hadron colliders, go up and up and up. This is LHC. But you see the overall trend even for hadron colliders is that even in the future, we don't expect that trend to continue forever. Basically, it kind of flattens out a little bit. While for lepton colliders, we go in opposite direction. So our energies go down in order to explore in enormously fine detail particles of interest like B mesons and other particles like super KKB, for example. So energy went down after approximately 1990s, 2000s, right? Currently, we know that we have 7 colliders operational. Overall, over the whole history of accelerators, we had built and made operational 31 colliders, and 2 colliders are now under construction. One is NICA, Hadron Collider in Russia. Another one is Electron-ion Collider EIC in Brookhaven here in the United States. And that's about energy. Energy, of course, is the most important characteristic, but not the only one. Collider luminosity is another very important characteristic, and you see that if first colliders had very small luminosity of the order of 10 to the 29, 10 to the 30, then we had approximately 1, 2, 3, 4, like 6 orders of magnitude increase in luminosities over the 66 decades. decades. The record luminosity right now set by super KKB just a month ago is 46.5 inverse nanobarns per second, or 4.65 10 to the 34 in our units, right? So, and what's remarkable, that luminosity grows by an impressive factor, right? 6 orders of magnitude. So, but it doesn't follow energy square. That's usually demand of high energy physics. So luminosity usually, progresses closer between like energy and power, well, like 1.2, 1.3 or something like that. And I can tell you upfront that this is what I've shown about colliders is actually not the most impressive development in the field of accelerators. Other applications of beams are showing such a tremendous progress that no surprise that society follows them much more closely. And those are, for example, if you look on the picture of peak brilliance in light sources or X-ray sources, and my microphone stopped working. It is working, right? So, okay. And that's from the year 1950. Again, approximately the same 6 decades. You see, they had 25, almost 25 orders of magnitude progress. In brilliance is number of photons per second, per millimeter square, milliradian, and bandwidths, and so on and so forth. So accelerator scientists were able to develop several techniques and several generations of light sources, 1, 2, 3, 4 generations. And recently we came up with a great idea of so-called free electron lasers, which deliver enormous brilliance of the flux of photons. Right. So that shows that, yeah, other applications of accelerators are extremely successful. Right. And to continue that message that accelerators right now serve much broader society than just particle physics, this is this plot. So what's shown here that in the past, how many, 3 decades, 2 decades, we show approximate total cost of the accelerator construction projects per decade. Basically collect everything we know about accelerators built between 2000 and 2010. And you see that in that decade, we built LHC, J-Park, Web 2000. So these are major high energy physics facilities, particle physics facilities. And we also had approximately $3 billion worth of construction of light sources, spallation neutron source, and so on and so forth. But look what happened in the decade between 2010 and 2020. So the investment in the particle physics facilities was significant, but significantly smaller, of course. It's under $2 billion. Super KKB, LHC, injector upgrades, so all goes there. But number of light sources, spallation neutron sources, XFELs, and so on and so forth is significantly bigger. And they already accounted for like $8 billion. So, and in the planning decade, that trend continues between now and 2030. So we plan to build so many, again, new type of light sources, XFELs, colliders for nuclear physics, electron-ion collider. And that's, you see, it's coming to close to 10 to 11 billion total, while investment in the high energy physics construction, high energy physics particle accelerators construction is going to be at the range of $2 to $3 billion. That includes upgrade of the luminosity called high luminosity LHC, PIP2, superconducting Linux, and LBNF construction. So what will happen in 2030s, 2040s, we still don't know. But again, there is a good chance to predict that that trend probably will continue one way or another. So and why we kind of stop or kind of why we have this picture. So why we have so many small accelerators and not that many big accelerators we are pushing for. Of course, one of the biggest reasons is the cost. Cost of accelerators is extremely touchy and extremely important subject. And we take into account if the first small accelerators, for example, for medical industry or industrial or security applications may cost between $10 to $30 million, then already large medical accelerator facilities could be $300 million. Third and fourth generation light sources will approaching $1 billion. X-ray fields in the range of 1 to 3 billion. Large hadron colliders and sub-TeV lepton colliders maybe up to $10 billion. And colliders we are talking about for our big bright future, breaking the limit of $10 billion. So that makes things extremely, of course, challenging. So, and to understand you that part of the challenge is not only just where we can make some difference. And we are showing this following slide. So the cost, of course, of big facilities, accelerator facilities set by the scale, larger, more expensive. Like if you have higher energy, longer and more powerful accelerator, it will cost more. But also it is set by technology. So, and there is of course the core technology, we call it core accelerator technology, like superconducting magnets, normal conducting magnets, superconducting cavities, normal conducting cavities, and so on and so forth. But we shouldn't forget that big part of the cost is involved in the civil construction. And that civil construction technology, we don't invent it. Basically, we take it from society. Whatever it costs, it costs. Same for example, for power delivery, transformation, distribution technology, right? So we take it from bigger world, right? So, and typically for big projects of accelerators we are talking about, the first part, that's where we can make difference, is accounts for approximately 50 plus minus 10%. And the second part is equally important. It's also another 50%. So even if you reduce costs of our, I would say, take your favorite, superconducting magnets to zero, still your project will cost a lot, because a lot of investment is required in the second part of the equation. Another important factor is timeline. So timeline, which becomes longer when you build big things. So bigger in size and cost of your accelerators takes a bit to longer time to build. So, and the timeline consists of three big components. Of course, probably there are details, but three biggest components are: pre-project R&D requires certain number of time, certain number of effort. And that strongly depends how novel the technology is. So if you want to build it on something well explored, you can start construction tomorrow, right? If it takes R&D in order to prepare your technology, industrialized technology, it takes certain time, right? That's a component number one. Second component is construction project itself. So, and if you have so many, I would say, $1 billion to construct, most of us do have certain limit on annual spending, and it's a very well usually defined limit. So you can go beyond, beyond something, and that sets the limit on how fast you can build your project. So, for example, this is a plot in the corner showing that for project construction time in years versus cost in total project cost $1 billion, or European billion Swiss francs for various projects. So LHC is somewhere here, smaller projects are somewhere there. And it's a substantial time. You see, it's between 3 years to 12 years easily, right? So another important consideration which we should take into account, we call it, that's a limit on available workforce. So in our community, we have kind of a rule of thumb, which we call Oide law. Oide is a famous accelerator scientist from KK, who kind of said that we need approximately one expert to spend intelligently $1 million per year. So intelligently keyword, yeah, of course, I can spend $10 billion a year, but it will be waste of money, right? So if you really want to minimize the cost, that's approximately how many experts you need. And remember what I told you initially, that we have only that many experts in the field accelerators worldwide, right? So that's a big limit. Consider, for example, ILC. So it's a $7 billion or so, or $10 billion, nobody knows, facility, right? So because we haven't built it yet, right? So, but it requires, of course, about 10,000 FTEs. 10,000 FTEs, it means over 10 years of construction, you need 1,000 people, 1,000 experts who build that collider. So, and if you have worldwide pool of 4,500, you understand the challenge, right? So where we get them. So final contribution to the timeline is commissioning. Commissioning takes time, and it strongly depends on complexity, and complexity is not just a word from the dictionary. So in accelerators, certain meaning. So it's actually, we understand very well what complexity is. And the past large colliders, the experience shows that, yeah, it takes significant time, on average about 5 years. There was, of course, some record fast colliders in the past, which were commissioned very quickly, but there were also colliders which took approximately, I don't know, 5, 6, 7, 8, even 9 years to get to the design luminosity. So we should take it into account as well. So that makes the timeline of big facilities extremely long, right? So now we go into the second part of the presentation. So how did we fare compared to previous P5? So in the previous P5 and Snowmass in P5, 2013, 2014, there were a number of recommendations in the final report, which was called Building for Discovery, and accelerator-related ones were: contribute to the LHC and helium LHC, engage in the LHC in Japan, contribute if it goes, build more than 1 megawatt proton source called PIP2. PIP2 stands for Proton Improvement Plan 2 for LBNF and Dune, and provide beams for G-2 METEOR experiments and reassess muon accelerator program and mice. I will say a few words what are those. In addition to the major recommendations of P5, there was a separate panel pulled together by HIPAP, which followed up these recommendations and approved several thrusts of Accelerator R&D. We call the general Accelerator R&D, like beam physics, sources and targets, what to do in the area of RF acceleration and structures, magnets and materials, and advanced acceleration. So, and again, we are happy to report that we greatly progressed along all these lines. So, of course, R&D continues, and it's always in process, right? But major recommendations are addressed pretty well. So either done or in progress. Situation with ILC is unclear, but we dutifully contributed to development of ILC. So we started construction of facilities for neutrino research and so on and so forth. So next slide summarizes it. So in terms of facilities and programs, we are contributing into the upgrade of the LHC called high luminosity LHC upgrade. We are building dozens of niobium 13, which is a new technology, niobium 13 quadrupoles, large aperture IR quadrupoles for high luminosity upgrade of LHC. So the project is already in the CD3 stage and to be ready by the launch shutdown 3. So and big laboratories are heavily involved in that. So we've started construction of a PIP2 LINAC, which is 800 MeV proton superconducting LINAC at Fermilab, with the goal of delivering 1.2 megawatt for the LBNF and Dune, and expect beam to be shoot in the next machine in the complex called Booster in 2029. And we are happy to report that approximately 30% of the cost is picked by our international partners, which is great news. So also we do have some great progress on muon beams for G-2 and Mu2 experiments at Fermilab. So G-2 experiment is already operational. Basically, we deliver muons. Good news, right? And soon Mu2 experiment will start running, and we'll deliver beams for them as well. So, and we have completed in between previous P5 and now, we have completed ILC program in the US with a significant investment. So the peak of the investment was and development was construction, installation, and test with beam, a first fully operational 1.3 gigahertz superconducting RF cryo module at Fermilab, where we demonstrated for the first time full specification of ILC acceleration cavities and structures. So in terms of Accelerator R&D, we were quite successful. Recently, many of you heard about records in development superconducting magnets. 14.5 Tesla magnet dipole has been demonstrated. It was part of the magnet development program. And again, that's magnets use niobium 13 conductors. We have finished experiment to demonstrate ionization cooling. So that was joint enterprise between US and UK and actually many other international partners. So in Rutherford Appleton laboratory, and that experiment has demonstrated 10% emittance reduction in one path as specified. At Fermilab, as another test facility called IOTA, IOTA ring has been built and now already kind of starts to report interesting results, like first ever demonstration of so-called optical stochastic cooling, yet another method to make beams a little bit smaller. And finally, we should say that our colleagues which work on the advanced methods like acceleration by wake fields in plasma, for example, or in structures, they have tremendous success. They first of all built a facility called FACET2, which is used for accelerator R&D. Uniqueness of facility is that for the first time ever, the beams with significant number of particles, like 1 nanocoulomb, 10 to the 10 particles, can be compressed in 1 micron by 1 micron by 1 micron object. So it's a super dense object of electrons, and at 10 GeV, that object can do miracles. And we have already a bunch of users lined up to use that facility. Another facility which we developed over many years called Bella. They set all kinds of laser plasma wake field acceleration records, like the record high gradient of acceleration. What is that? It's 8 GeV over 0.2 meters. Quite impressive, right? So, and recently they demonstrated staging of this laser plasma acceleration stages. 0.1 plus 0.1 GeV been demonstrated. Okay, so that's what we've done since previous SNOMAS and P5. Now we go into the what do we see now happening in the field, and where do we see the field going to in the next decade? So we got input from our topical groups, and they provided our own input to community in P5, and we evaluated options on the various future facilities. So we start with facilities for neutrinos, accelerators for air processes, and colliders. So start with the facilities for neutrinos. Of course, we again said 3 times already that Fermilab is building this superconducting LINAC called PIP2. And again, this is webcam, picture taken just yesterday. So, and the question is, of course, after, what's going to happen after? So in 2030, so what do we plan to do with this facility later on? So, and the answer is following. So what we hear from our colleagues from Neutrino Frontier or those who plan to use that facility is that what we plan to deliver for them in 2029, 2030 isn't enough. So what they originally asked for is what they call project phase 1, that based on 1.2 megawatt proton beam, that's what we are building our facility for, good near detector and 20 kiloton liquid argon detector in the far side at South Dakota. Now they shoot for phase 2 in order to get faster to discovery potential. So they estimated that in order to get to 5 sigma discovery, they need at some moment to go through significant upgrade, phase 2 upgrade. That will require to go to improve beam power from 1.2 megawatts to double it to 2.4 megawatts. On top of that, they will need new near detector and extra 20 kilotons of liquid argon. Right. So how to get to 2.4 megawatts? So that's a question for us, and we ask ourselves and our community what we can do. So if you look in the accelerator complex at Fermilab, you see there are many machines, many beam lines, and ask ourselves, so how to get from 1.2 to 2.4 megawatts in the LBNF neutrino beam on target? Question is that there's probably no problem with the biggest accelerators. The problem and bottleneck is found to be at the low end accelerators, particularly in what we call the rapid cycling synchrotron called booster. So in that booster probably will prevent us from doubling up the power at the end because of problems at injection energy and transition crossing limit. Transition crossing is special topic when beam goes through special energy, gets berserk, so losses essentially. High energy beam is lost and it's extremely bad. So, and the same happens at ejection energy. When you eject the beam, space charge forces blow up the beam and you have losses and it's bad. So there are two proposals how to get around that bottleneck. So one proposal is to build a better modern rapid cycling synchrotron. So basically you have PIP2 Linac as given, right? So we build it by 2029. Then build a modern rapid cycling synchrotron, which will not have problems with either injection or transition crossing. We can do it because we know now how beam optics and how beam dynamics plays, right? So, okay.
Apologies, we got requests to turn on the captions. I know you didn't want them.
I didn't want them. I still don't want them. Okay. You see, the slides are so dense that there is no spot even for. Okay, fine. And of course, that new rapid cycling synchrotron, which will accelerate particles from 1 or 3 GeV injection energy to 8 GeV, will be more than sufficient to provide enough beam for main injector acceleration and 2.4 megawatt upgrade. So that's option number 1. And option number 2 is just to go straight, forget about any rings, and use superconducting Linac all the way to the injection energy in main injector, so bypass all the rings, right, and inject in main injector, and again, you can get 2.4 megawatt, right? So what should be taken into account when we talk about these upgrades? There are challenges, of course. Nothing comes for free. First of all, we should all be sober about competition. We are not alone. So we have a Hyper-K program fed by beam from J-Park facility. Again, these closed captions are extremely, can we move them? Extremely unwelcome in this talk. Right, move them, sir. Move to the left lower corner. Oh yeah, fine. That's, yeah, leave them here. Right. Then, okay, even better. No, to the left. I'm serious. Move it to the left so it doesn't interfere. Okay, point is that look at that picture. It shows that average beam power on target for 2 major leading facilities in the world. One is Fermilab main injector complex, which delivers beam at 120, and J-Park in Japan, 30 GeV beam. So what matters, this is of course years, right? So we right now have a record for average power of 893 kilowatts on target, and they have 515 kilowatts, but they have extremely aggressive upgrades coming. So basically very soon we believe that they will cross even 1 megawatt line and kind of go over us. That's where our upgrades, 2.4 megawatt upgrades, will be extremely helpful. We definitely help our scientists to get further ahead with the discoveries in neutrino sector. So it's number one is competition. Number two is we have really short timeline, and there are a number of design questions. Many of them depend on what else you want to do. So you understand that in general, so these big facilities cannot be always used for something, just one experiment, right? So we want to figure out how to make sure that when we design something, later it can be used for something else. For example, for mu2E2, for dark matter and rare processes searches for muon collider or something else. Then, of course, there is a cost challenge. Of course, the rest of the complex will need to be upgraded as well. It's not just this bottleneck to be fixed, but also main injector RF will need upgraded and so on and so forth. 2.4 megawatt target. That's something that we don't have yet in hand. So performance risk is there too. So there are potentially beam losses in various machines caused by instabilities, injection, collimation, space charge effects. We already carry some R&D in the IOTA test facility at Fermilab. But again, these are all important questions we should be taken into account when we make decision how exactly we want to get to 2.4 megawatt. Okay, now my slide change doesn't work because we need to click every time you move this black caption. Yes, so stay next to computer, please. Okay, click. Okay, now it works. Switching gears to accelerators for rare processes physics, right? So again, looking through SNOMAS white papers, there are many. So our colleagues in a corresponding topical group figured out that there is a lot of interest for accelerator facilities needed for dark matter searches, axion, EDMs, charge selector favor violation experiments, muons, light mesons, beam dump experiments. There are calls for corresponding beam facilities at Fermilab, at SLAC, at JLab, SNS, and there is a variety of beams which can be used and should be used for these searches. Starting with the electron beams, GV or multi-GV electron beams, to proton beams of all kinds and energies and time structures. So quite diverse set of requirements. And you see, I don't, of course, have any time to go through the list of possible experiments. It's enormously long. Our previous two speakers showed you how many things they have in mind. We still don't know what exactly might work or might not work from point of view of our colleagues in accelerator field. All right, so in many cases, existing or planned facilities can be and should be fully utilized. That's a key point. So if you have facility for neutrino research, why don't you try to utilize it for something else? An excellent example is SLAC, right? So with a relatively small investment, there is a project already ongoing, a laser beam line for LDMX at SLAC. So almost parasitically, they plan to use SLAC electron beam at 4 to 8 GeV coming out of superconducting RF LINAC. Yet it will be low intensity, almost CW beam line, and it will serve a LDMX experiment. The construction is started. We think that many experiments can also be almost parasitic, but some require minor investment. For example, one of the greatest idea come so far was, can we build parallel to injection into the booster? Can we use PIP2 LINAC beam and reshape it properly so it can be used for dark matter search experiments, for example? So the beam coming out of PIP2 LINAC is expected to be long, approximately 1 millisecond every, I would say, 10, 20, 100 hertz or so on and so forth. That's not what dark matter search experimentalists want. They want few pulses with extremely high charge. So basically, the beam structure should be reshaped from flat to 4 distinct short pulses. And that can be done by injection in what we call PIP2 accumulator ring. So that's the ring, which is like a figure 8 folded, right? Which can do exactly that. So you inject into the ring many of these turns of H- particles, turn them into protons and extract them one by one at certain time. So it's a great idea. Can deliver up to 100 kilowatt of power for dark sector program at 100 hertz. And again, we hope that it will find interest among you guys, and P5 will support it, right? So now switching gears to particle colliders, it's topic number 3. Very important that there are too many collider concepts to cover in any detail. So brief technical descriptions can be found in RMP and PDG. Detailed evaluations are also available in our topical group reports and ITF report. I will say you what ITF is about, and all available through this Accelerator Frontier website. So there, it's most important is to figure out what do you guys want. And the first slide we always start with is the Energy Frontier draft report. What do our Energy Frontier colleagues want? And they clearly spell out that in each period of 5 years, starting 25, starting 2030 and 35, what do they want? Targeted A plus A minus Higgs factory detector R&D. Develop initial design for first stage TEF scale muon collider in the US. Detector R&D toward multi-TEF colliders, E plus A minus Higgs factory, first stage TEF scale muon collider, Higgs factories, first stage muon collider. So again, basic message is they want Higgs factories or factory, 1 or 2, I don't know how many, and multi-TEF muon colliders. That's message which we clearly got, and I will address it one by one. But besides just what we heard from Energy Frontier, we got input from other sources. For example, just a couple of days ago, you've heard reports from our E plus A minus Collider forum, which was jointly organized by Energy Frontier, Theory Frontier, and Accelerator Frontier. They looked into options for Higgs factors and figured out that FCCE and CPC, they can deliver significant luminosity. Of course, they are a little bit more expensive than, for example, ILC and CCC, which could be built faster and probably less costly. And US should contribute to any Higgs factory which region A, B, or C will be committed to. So basically, they call for collapse of wave functions. So if someone decides to build something, we should be part of it, right? So, and of course, they mentioned that for speaking about 10 TeV scale colliders, E plus A minus colliders, Wakefield accelerators will need to continue R&D toward closer to colliders, to become closer to colliders. So mu plus mu minus collider forum is another organization where Energy Frontier, Theory Frontier, and Accelerator Frontiers work together. So, and their statement is that 10 plus TeV center of mass muon collider is ideal machine. They see no showstoppers, and the best performance in terms of luminosity per terawatt hours, and relatively inexpensive, still expensive. You will see the numbers later. They will need significant engineering effort and some targeted R&D. They actually call to development of pre-CDR by 2030, establishment of US Muon Collider Organization, and joining international collaboration already created at CERN by European partners called International Muon Collider Collaboration, IMCC. Implementation Task Force is another organization. I will say a few words about the organization that later on, but they evaluated 32 collider proposals, which are currently on the table in terms of cost, schedule, technical readiness, power requirements, physics reach, and they didn't, of course, make any prioritization of any kind, right? And finally, we recently got a very interesting initiative called US National Collider R&D Initiative. They claim that there's, and they correctly claim that there is a gap, significant gap in accelerator R&D in this country towards collider facilities of the future. So, and they call to establishment targeted program in the Office of High Energy Physics and take integrated approach to cover international efforts like ILC, FCC, international muon collaboration, and toward US options feasible in the US, like C-Cube, Helion, 10 TeV muon collider, et cetera, et cetera. So let's go through various proposals. If you start with Higgs factories, the most matured ones, again, the list is not prioritized, so read carefully. And I will just very briefly go through advantages and challenges. Advantages, something positive. Challenges is something less positive, right? So, and we start with FCCEE, which is a 100-kilometer long collider, and CPC, similar type of collider to be placed in China. And their big advantage for FCCEE, for example, is that it's already been supported by European strategy. So they strongly push for it, and CERN is behind the program. They started feasibility study, and that collider promises significantly higher luminosity than any other Higgs factory. But on the other hand, this FCCE is the longest one, quite expensive, and again, power consumption is one of the challenges for that collider. CLIC is another machine. It's a linear collider, requires a normal conducting RF at approximately 72 megavolts per meter, but it's still 11 kilometers long. It boasts the lowest power consumption, and it's the shortest of all these three machines. It is based on relative novel two-beam acceleration scheme, which probably can be replaced by clusterons if necessary at some expense, and very tight tolerances on everything: RF stability, transverse positioning, jitter, and so on and so forth. So last but not least, by any means, is the International Linear Collider, which we all know for many years. It is ready to go. Physics-wise, it has great advantage of being a collider which collides polarized beams of electrons and positrons. Both beams are polarized. But if you look into the scheme, so the scheme shows that the ILC is 21 kilometers long because gradient is relatively small. So it requires a significantly sophisticated positron source. And again, we're all waiting for some positive news from Japan in order to start contributing more actively into ILC. Interesting new developments, that's why I said new, are a couple of linear collider-based Higgs factories which can fit Fermilab site. So of course, if Fermilab site is limited, it's about what 4 by 5 miles, and the maximum diagonal length is approximately 7 kilometers. So in order to fit Higgs factory on Fermilab, including beam delivery system, I need gradients approximately 70 MeV per meter, right? And given that that will be relatively compact collider, it will potentially cost less. And there are two great options which we consider in some detail and actually strongly support further considerations of them. One is called cool copper collider, so which is based on normal conducting RF cooled to the temperature of liquid nitrogen, 77 K, and at 5.7 gigahertz frequency with proper klystrons, they will be able to deliver 70 MeV per meter or even probably more. Another option is called Helen, that is a traveling wave ILC type collider. So basically, after modification of a structure of ILC superconducting cavities, they can achieve these gradients at 2 Kelvin and frequency 1.3 gigahertz. So it's basically substantial change of RF technology, but quite feasible. Basically, you don't probably need even to change cryomodule design of the ILC cavities, right? So these are two facilities. Other more aggressive alternatives include energy recovery based plus and minus colliders, circular or linear. So energy recovery, it means that you can use your beam many times and recover energy after collision. Basically, you collide particles and then return them back, ask them to send back their energy to RF cavities, and that's the way to reduce power consumption. So these approaches show promise of high luminosity per megawatt power consumption, but in general they are not yet mature. So their technology is orders of magnitude in beam current which they can circulate, and the quality factor of the cavities needs to be significantly improved. This machine is usually long and expensive. Other approach is gamma linear colliders. When you collide, instead of E plus and minus particles, you collide two gammas, right? You bring your electron, for example, or from one side, convert that electron into the photon, and let photons collide with each other. In that S-channel collision, so you need only half of the energy. That makes everything twice shorter, right? And potentially less expensive, and you need no positrons, which is one of the big problems for other colliders. So of course, the disadvantage or challenge is that they need two beyond state-of-art FELs to generate gammas to collide with positrons. And again, beyond state-of-art means significantly beyond what we can achieve right now. So significant R&D will be required if you go that way. Muon collider Higgs factor is another option which requires only half energy. It's very compact, less expensive, but it's too long to develop because it requires like say 10 years or more of time to fully demonstrate muon cooling. And again, it does have small luminosity, but cross-section of muon collisions in this channel is factor of what, 40,000 higher, right? So if you switch gears to much higher energies, energies of the scale of 3 to 10 TeV per constituent, per parton, then the options are many as well. So most discussed options are click, basically extend click technology, increase gradient of the click technology to 100 MeV per meter. And in 50 kilometers footprint, you can get to 3 TeV. And what's good about this proposal, they have very well considered, thoughtful conceptual design report. Demonstration facility has demonstrated essentially the gradients and what else is necessary. But again, as I said, 50 kilometers is long, facility is expensive, and huge power consumption approaching 500 to 600 megawatts compared to approximately 200 megawatts of CERN site, right? So another opportunity is FCCHH, that is 100-kilometer long hadron-hadron collider in the tunnel of preceding E plus and minus collider, right? So if you put superconducting magnets, approximately 16 Tesla magnets are required, you can get to very high energies, right? Of course, these facilities will definitely get much higher luminosities, and they have significant help from the LHC experience where we understand how these beams behave, proton beams at high energies and high intensities. But experts estimate that approximately 2 decades will be required to develop the 16 Tesla magnets, not as a record demonstration, but as an industrially available magnets, right? Parts of the collider. Yes, these colliders will be expensive, and they also require significant electric power, right? So same for collider SPPC in China, proposed in China, right? So they shoot even for even higher energy magnets, 20 Tesla magnets. That will require another, I would say, qualitative leap in technology. Instead of niobium-13 magnets technology, they will need to go to what they call iron-based superconducting magnet technologies. That's something we haven't seen before, right? Finally, muon colliders are compact. They, for 10 to 14 TeV center of mass energy, the collider itself is about 10 to 14 kilometers long, still requires 12 to 16 Tesla magnets, potentially lower cost, best luminosity per terawatt hour performance, significant engineering effort. That's what these captions don't show us, and development on many subsystems is required. So R&D on muon cooling is necessary, and development of such system, because there are many of them, from targets to acceleration to magnets to fast ramping magnets and so on and so forth. Right. What's interesting about muon collider that potentially one can consider siting it at Fermilab. Again, the largest circle you can fit into the Fermilab site is approximately 16 kilometers long. That allows 6 to 10 TeV center of mass muon collider. And again, that's been seriously considered as one of the options, and people kind of we are very glad. It's in one of our white papers, this proposal being described in quite detail. So other ideas for energy frontier proposals include some simplified approaches. For example, you take certain technology and push it to the limit. For example, ILC, nothing for potentially, or at least could stop us to extend its energy to, for example, 3 TeV or more, right? ERL-based colliders can be also extended to 3 TeV. One most interesting proposals was, say, let's build collider out of the cheapest possible magnets, but with the longest possible circumference, like collider under the sea. 2,100 kilometers will deliver you approximately 500 TeV center of mass energy, right? So what's the problem with these colliders? That usually they are long, they're expensive, and power consumption is just goes beyond anything we can imagine, right? Wake field acceleration in plasma, by beams, by lasers, linear colliders based on these technologies. Definitely they will be most compact, maybe cost efficient. We still don't know yet, because it depends on how expensive or inexpensive your drivers will be, and may potentially offer a good way to multi-TeV collisions. Of course, there are many uncertainties. Uncertainties right now they're in the range of physics of acceleration of positrons, staging, beam quality, power efficiency. So a lot of R&D is required, and we, as you've seen from my previous slides, a lot of R&D already been done. Right, so EP colliders, EP EH colliders like LHEC, FCCH, and so on and so forth, definitely would be probably the most cost efficient. So they are really inexpensive. So if you have great big proton collider and you put approximately like few kilometers long energy recovery recirculating linac next to it, so you can arrange really high luminosity collisions at the center of mass energies between 1 to 3.5 TeV, maybe even to 5.5 TeV. It will be a very nice addition to proton machines, and very feasible, really inexpensive. But this high current 50 GeV RL technology still needs a demonstration. So if you compare where we are now and where they want to be, there is a gap approximately 3 orders of magnitude to power, which is really big when it comes to powers. That's why you see there are so many details, so many proposals, and in order to figure out in more or less coherent fashion with this on the same basis whether there are any advantages and disadvantages of various proposals. So we pulled together the Accelerator Implementation Task Force, which was charged to develop metrics and processes to facilitate comparison between collider projects. So this is composition of the task force. So 12 accelerator experts from US, Japan, and Europe. We are joined by 3 liaisons to Energy Frontier, Dmitry, Meenakshi, and Lian Tao, and Theory Frontier, and 2 our SNOMAS young partners. And we addressed physics reach, size complexity, power, environment, technical risk, technical readiness, R&D required, and cost and schedule for all these many 3 dozens of approaches. A report is published, available through Accelerator Frontier wiki page. So if we look into this, there are many tables. Thomas Roser gave a talk on Monday, so you showed many detailed tables. I summarized them in one, which is of course I'm missing a lot of information. So, but take for example Higgs factories, FCCE, ILC, and CLIC, kind of most matured projects, right? So you see that they have their kind of luminosity numbers here, and FCCE has the highest of them, right? Then years of pre-project R&D. So this indicates this 0 to 2 years indicates that essentially this project, essentially you can start, talking about them and building them right now, right? But years to first physics, that includes industrialization, construction, and commissioning, varies a little bit. So for ILC, it's less than 12 years. It's probably the best way, the fastest way to get to Higgs physics. While for FCCE and CLIC, technically limited schedules are at the range of 13 to 18 years, right? The cost ranges are different slightly. FCCE is in the range of $12 to $18 billion without escalation, without contingency, while others, ILC and CLIC, are less expensive, and power consumption numbers are listed here. So more, I would say, novel approaches like Helion or C-Cube or ERL-based approach when you put the ERL accelerator in the FCC-EE tunnel are listed here in black color, right? So those three. And you see for them that the cost estimates, cost ranges are different. Time required to carry out R&D is different too. For example, for C-Cube, it might be 3 to 5 years, while for Helion and CRC, 5 to 10 years. That reflects also in much longer time scale for first physics and power consumption numbers. Pay, for example, attention for the energy recovery would allow you to significantly cut power consumption in principle, right? If you look into the high energy colliders, the situation is quite different. So all like CLIC, ILC, 3 TeV, and Muon Collider at 3 TeV, they are all expensive. 18 to 30 billion, 18 to 30 billion, 7 to 12 billion. Takes significant time. The longest time probably will be required for Muon Collider. Still years to first physics is in the range of 19 to 24 years. And power consumption, Muon Collider shows its advantage already at that energy. At much higher energies, again, you need significant time to develop technologies for multi-TeV, 10 TeV colliders. Either it's Muon Collider at Fermilab or Muon Collider at CERN or FCCHH, which is covered by this black bar. Right, and again, the years to first physics varies between 19 to 24 to more than 25 years, and the cost ranges are shown here: 12 to 18 to 30 to $50 billion for FCCHH, and power consumption is, as I said, pretty high for FCCHH and relatively low or modest for Muon Collider. So, takeaway from the enormous effort put together by these 15 great individuals is following. ITF takeaway is that ITF reviewed concepts to allow comparison, but didn't prioritize. So it wasn't their job. ITF did not review luminosity and power consumption of these projects. That is, again, requires much more serious discussion about what you can get with certain techniques. Number 3, that ITF recommends, and we support them, that R&D to reduce cost and the energy consumption of future collider projects should be given high priority. And finally, ITF evaluations could be updated on a regular basis if necessary. So this message about power reduction particularly comes from this plot pulled together by Spencer Gessner, so who shows that various collider types, for example, circular plus or minus colliders, ERL-based colliders, linear colliders, Muon colliders, Wakefield colliders, and Hadron colliders, they have different sensitivity when you try to increase the energy. If you try to increase the energy, for example, of circular plus or minus colliders, very soon after Higgs energy, the power luminosity efficiency, luminosity Barnes, inverse Barnes per terawatt hour, drops down very quickly. For ERL-based colliders, the range is expanded a little bit on the right. So for hadron colliders, because hadrons start to radiate at very high energy, efficiency goes down as well. So the only concepts which stay flat are linear colliders or Muon collider. This is pink line that grows with energy. So that kind of gives us food for thought. Our final message, we are approaching the end. So it's what Accelerator Frontier kind of want to communicate to the bigger world, to P5, to SNOMAS. So, and it's following. So first of all, we've heard from Jan Hewitt earlier at this meeting that we done so well compared to previous P5. This is previous prioritization kind of projects shown in one plot. So, and you see many projects and experiments turned from green and completed, from blue to constructed and operation, from yellow, from design to construction operation. Basically, we don't have many projects and experiments and ideas to plan for the next decade, right? So that's where we are right now. So you see just 2 yellow bars left. So there are not enough, I would say, proposals, serious proposals on the table. And our message, number one, I think I convinced you in my previous 30+ slides, that we have a broad array of accelerated technologies and expertise to design and construct prioritized HEP accelerator projects, whether it will be for neutrino physics, for rare processes, or for energy frontier. Message number two refers to colliders. We need an integrated future collider R&D program to engage in the design and to coordinate development of next generation of collider projects. That program will address in integrated fashion technical challenges of promising future collider concepts that are not covered in the existing general accelerator R&D program. That initiative will enable synergistic US engagement in ongoing global efforts like FCC, ILC, and International Muon Collider collaboration, and develop collider concepts and proposals for options feasible to be hosted in the US, like C-Cube, Helion, Muon Collider, etc. Take a look at this picture. So it shows over the past 10 years, the sum of investment by Office of High Energy Physics, HEP, Advanced Technology R&D budget in $1 million per year, from 2012 to 2022, 23 request. And the first part is in gray, is money which go into the support of accelerator test facilities, operation and construction. Red one in the past used to be called directed R&D, and the blue one is general accelerator R&D, basically accelerator research, development of various tools, beam experiments and simulations, and so on and so forth. And you see that these red bars are vanishing very soon after previous P5 because of many reasons. ILC, our investment in ILC got reduced. We have completed LHC accelerator research program, which was targeted toward making luminosity at LHC faster, or higher luminosity and sooner, right? And US Muon accelerator program was reassessed. That's the language from P5. In real world, that means closed, right? So, right. So, and afterward, so what we see is there is no directed R&D left, and exactly what this initiative, which I was talking on the previous slide, is about. They propose to restore stream of funding to support developments towards future colliders in the next 7 years till 2030. So by 2030, we as a community will have definite, more or less, I think probably more definite descriptions of what these facilities are, and that will empower us to make some informative decisions. Right now, we are not in the position to say anything is essentially about the many, even most promising of these collider options. But this National Collider, Future Collider R&D Program initiative will supposed to help us to be ready to say something definite by the time of 2030. Right, and as I said, it has a number of components to consider, at least the proposal. And I think it will be very, very important and critical for our field to have it supported. So message number 3 is that we have an ongoing R&D program aimed at fundamental beam physics and long-term level of accelerator concepts and technologies, RF, magnets, beam physics, advanced concept. All these items have broad applicability across future accelerators via ideas from universities and labs. And this R&D is key to facilities for neutrino and rare processes and colliders. So basically, general accelerator R&D is something we have to continue one way or another, because they are important to keep us afloat and be not necessarily dependent on approval or disapproval of some project or another project. So accelerator R&D, as I said, in the US is quite diverse. There are many components. One is multi-megawatt targets, and for the next decade, our colleagues saying that they're focused on developments of, first of all, targets for 2.4 megawatt proton complex upgrade at Fermilab for what we call PIP3. And they're thinking about how targets for 4 to 8 megawatt targets can be designed for future, for example, facility like a Muon collider. Our aspirations in terms of magnets for colliders and rapid cycling synchrotrons include development of 16 Tesla magnets, 40 Tesla solenoids, 1,000 Tesla per second fast cycling magnets. And we definitely believe that should be very well coordinated with the existing US magnet development program. Our colleagues working on the technology of superconducting, normal conducting RF put quite impressive goals to demonstrate 70 to 120 megawatt per meter acceleration as needed, for example, for CQ project, or in the traveling wave superconducting RF project. They plan to develop over the next decade new materials, which will allow us to have much higher quality factors, basically smaller heating and power efficiency, efficient RF sources, and Wakefield accelerators will shoot for collider quality beams, efficient drivers and staging, and they plan to work in close collaboration with our international partners, for example, as those activities supported by European roadmap and EPROXI. I'm stopping. And the last slide is that Accelerator in beam physics assumes that we will plan research on high intensity, high brightness beams, high performance computer modeling and applications will be developed, and we call for investment in the design, integration, optimization, including energy efficiency. Beam physics is overarching for all our efforts. Final message is that workforce-wise, we need to strengthen and expand educational training programs, support university-based research, encourage labs to accept more traineeship students, including international ones. Surprise, surprise, it's getting harder and harder to get international students. Wrapping up, finish up, last message. Accelerator development should be part of P5. Planning for accelerators should be aligned with the strategic planning for strategic physics, for particle physics, and should be part of P5 prioritization process. Thank you for your attention. So we have time for a few questions, right? Excellent. So questions come from Zoom, from audience, and Google Doc, as far as I understand. And Steve and Tor, could you please help me and answer? No, you want to stay? I don't want to be alone on stage, you know. These guys wrote from upstairs, and I just messaged deliver.
Sorry?
Okay. Yeah, sit. They need a microphone, by the way. They need microphone.
Should I go ahead and ask? Okay. Yeah, kind of following up on our discussions this morning, some of the issues that came up that we made and Sergey made a strong point about the importance of having an organized program at PIP2, both in PIP2 as it's going to be built and possible upgrades depend on having a physics program. And I realized as I was watching it, it doesn't really fit here because most of that is not inherently accelerator development. It's effective usage of what's going to be there and then making the choices for the next step. Like you mentioned, the accumulator rig. You know, there's a program that doesn't need any of that. The next generation charge lepton failure validation. And the question is, we think that's very important to have that program that was identified. Where does that go in the SNOMAS process?
So I think the issue there, and it's a very good point, right? But it's a mix between helping define what the physics program, the physics defining what the program is, and then feeding back to the accelerator to help orientate what the upgrade for PIP3 should be. And that's what, you know, Vladimir mentioned that as a big issue, because figuring out how you do that will impact on what experiments you can run. But you need to define what the physics is that you want to do first. And actually, I guess you have to do it in parallel because different upgrade approaches have cost impact.
Sekar.
Hi, Sekar Chavukala, Chair-elect of DPF. I just wanted to say, and this is for all of us in the audience, I understand how frustrating it is to deal with the captions and the limited technology that we have, but it is absolutely essential. You know, I want to congratulate Gordon and Shichi and the others here for making the effort to do the captioning to enable all members of our community to equally participate. And I realize it's really frustrating.
It is.
But you know, that's a technological limitation, but imagine how frustrating it is if you can't actually understand what's going on in the wonderful talk that we just heard. So let's not do that.
Hitoshi.
Thank you for all the work you have actually put into this. I really appreciate it. And one comment you made about the need for the integrated R&D program, that does appear to be essential for the future. So I tend to agree with this. And the word integrated sounds nice, but what you said looked like a little bit on everything. And is that the right way to do it? What does actually integrated mean in this context?
Sorry, the integrated collider R&D program. So that it was we've gone to DOE and talked about supporting individual projects, and DOE is not interested in doing that. I've gone and asked for funding for FCC. Other people have gone and asked for funding for a muon collider. They're not interested in doing that right now. What they are interested in doing is finding common themes, tools to support the idea of designing lepton colliders, whether it be E+, E- or muon colliders. Collimation, again, it's a common tool or common issue that we have for all these different things. Beam instabilities, high power RF or efficient RF sources. And so finding common themes like that, I think, is critical. And then as part of that, ultimately we'll be in a position to start doing design studies where we do an integrated design study for different concepts. And if you get the people, I mean, one of the things that we're doing is we're losing people that know how to design a collider, right? A lot of the people that did all the work on ILC, they're gone. We've lost an enormous amount of resources in the US for people to do that work. And yeah.
Me? Okay. Thor, I'm here, but any of you can answer, I suppose. But the point is, how do we get our other communities from basic energy sciences who benefited a lot from the past accelerator contributions from high energy physics to contribute for future of in favor of, let's say, building a collider, which is more for high energy physics? I don't know how the plan can, how HEPAP and P5 can recommend something which will go beyond that. But I think that in the SNOMES process, we should be able to say that, you know, the broader community has benefited from high energy accelerator development programs in the past. You should now give back a little bit to us and it'll be good for all of us, right? At least for the electron colliders, that should work.
So I think there's an element of truth to that, but one needs to be very careful. You know, some of the big work that has happened in SRF technology over the last 5 years was funded by BES. Okay, it took the cavities that were designed initially for ILC and improved the Qs by over a factor of 2. And that's all funded by BES. It doesn't appear as a BES R&D project. It's part of a construction project. Nuclear physics is doing lots and lots of R&D to support EIC, but it doesn't appear as accelerator R&D. And so it's part of the EIC construction project. So it's a little hard. Your basic concern, I think, is correct, and figuring out how we can get more funding explicitly into the BES program or into some separate office of science program. You know, there is this new stewardship office, which is aiming at that. Right now it has little funding, but hopefully that will increase. And that may be a path. We can certainly augment that.
Thank you. Thank you very much for this nice presentation. So I was one of the chairs of the Electron Positron Collider Forum, and we were very surprised. I'm very glad.
Could you drop your mask, please? It's
so I'm one of the co-chairs of the Electron Positron Collider Forum, and we were very surprised about all the ideas, new ideas that have been proposed for electron positron colliders. As you mentioned, some of them are more mature, some of them are less mature, but it may be very useful to define a strategy on what R&D would be needed to bring some of these technologies to another level of maturity. So for instance, you mentioned one of the things that many of these accelerators are very consume a lot of power, okay? So try to define the roadmap of what accelerator R&D would be useful to bring the technologies to another level that may already be good starting point when going to request for funding to funding agencies.
So that is something that we will be doing as part of the report as best we can. There are some common themes. I mean, you heard multiple times that high power or efficient RF power sources, high Q cavities are very important. You've heard about the normal conducting RF, cryogenic RF, that being a big step. We can try to map that out, but at some level, there's going to have to be some prioritization that happens. We are not, you know, this is SNOMES. We don't prioritize here.
So, yeah, so let me add to that. Of course, you're aware there are many other factors in deciding what gets built where, right? And I think part of our job as a community is to make it an easier decision by giving them more options, because there's geopolitical, there's all sorts of things. So it's going to be up to the next step to decide that, and the one beyond.
Yeah, so you've made the case that a significant fraction of the cost has to do with civil construction and tunneling. But then I see these diagrams of site filler colliders on the Fermilab site. And so my question is, how seriously should I take that as Fermilab specifically, or does it make sense, or are other sites being considered, like a greenfield site?
Jeff, short answer is that everything that we've shown today should be taken very seriously. Okay, and we talk about details later. So actually, we're looking more for more questions from our non-accelerator community, basically particle physicists, cosmologists, astrophysicists. So please ask us what you're interested in. And okay, go ahead.
So I'll follow up on the comments from before. For a long time, people had the impression that accelerator R&D could be used in part to reduce costs. And seeing, I don't know if that was taken into account by the implementation task force or not. And if not, which of the R&D programs would be most likely to reduce costs from, say, $12 billion to $8 billion?
Steve?
I don't know. No, that's a very good question. It depends on the nature of the accelerator. You know, if it's a linear collider, then more efficient RF sources and cavities would be the way to go. If it's a big collider, then the magnet technology would be the way to go. So it really depends a lot on what type of machine you're building.
It also depends on what time scale you're looking at. So, you know, for example, the linear collider programs, ILC and CLIC, put out design reports in 2012. It's been a decade since then, and there are new ideas. You heard about one, which is Helen, which is a superconducting RF-based one. Another one, which is C-cubed, which is using normal conducting. Both those technologies have advanced a lot in the last 10 years, and you can apply that. And Vladimir mentioned that, you know, we're not in a position where we can evaluate the costs of those projects directly, but there's certainly a savings involved with using the new technology. Is it 10%? Is it 20%? We don't know exactly, but it's something. If you're looking further out, you know, maybe if lasers become substantially cheaper, then laser-based acceleration could be a path. But there has to be huge advances in that technology, and you probably have some time to do that.
Max?
Vladimir, I have
Oh,
a microphone
Okay,
already.
sorry.
Gustav Boymans, Columbia. Vladimir, you had a slide already with R&D investments that are made, and you showed that directed R&D has died off as those directed projects completed. But there's still something like $60–70 million of R&D every year. Is that correct?
This one?
Yes, that one. So can you tell us something about what that R&D actually entails? Is some of that, or so for example, a project like C-cubed, does it already appear in there at some level? And does it become, if there's a recommendation, does it become something that is part of the gray or blue? Does it become led by Fiat?
The short answer is that everything that we know today as a promising technology of the future came from these activities. For example, C-cube idea came out of initial studies dedicated to kind of how much of performance of normal conducted cavities can be pushed, or initial superconducting RF cavity development tapped out of this pool, or these new ideas like optical stochastic cooling or crab waste. They're all being supported by this pool. So what we're trying to convey in the message number 4, that this is super critical, super important, because it basically keeps us afloat. If you want to finish your life 20 years from now, stop that program. That will be the best way to kill everything at once. So
let's see. I believe there's a question on Zoom. Can I?
Gordon, how to unmute Zoom attendees?
Oh, you're on the.
Can I go ahead?
Yeah.
Okay. Well, one of the questions which I'm here. One of the questions which I wanted to discuss is related to what we becomes now more and more, how to say, on the agenda, not only science agency, but beyond the question of sustainability. Of course, sustainability of future accelerators and facilities. I mean, in terms of making in power efficiency or improving the coupler efficiency, this is one of the elements. Another element is actually, I mean, there is a lot of work in accelerator design which is done, is related to general question how we define sustainability, because sometimes when you try to identify it, the question comes according to which ISO standards, for example, are you define sustainability, etc. Do you see the way that this word sustainability can be also in consideration, can be used to more direct fund, extra funding, directed funding for the accelerator R&D in order to cope with the global agenda and somehow to make a showcase of what our domain is doing in terms of sustainability, because here and there are a lot of elements. Is it going to be addressed somehow, considerations about this?
So in the report, I don't know if we're going to try and address that. There is an ICFA panel on sustainability, which is looking at these questions and looking at how one can motivate and get additional funding into the field. Whether we put something in the report or not, we have not yet discussed. I think in the US, we're
Could you repeat his question. In the
Oh,
US.
the question was, is there anything explicit happening in the US? And I guess the short answer is, I don't believe there's any explicit change happening in the US. We're going to put a recommendation that we consider this more strongly in the US.
There is one,
But I don't know if
there is one example that's to make more efficient RF sources, clystrons. So basically, if you improve efficiency from 50% to 80%, you save enormous, money and power.
It also comes directly back to the cost of the project. I mean, if you can save money by putting in less infrastructure, that's a significant saving. As Vladimir pointed out, that's 20% of a lot of these projects.
Alex,
Do you have anybody from Zoom?
Yes, Alex
Yes.
Riedman.
Can you hear me?
Please unmute yourself and ask your question.
Yes, certainly. So I was curious whether the Accelerator Frontier has any plans to call out taking advantage of the recent availability of large quantities of high temperature superconducting tape on the commercial market in the magnet development program, or is that part of one of those US magnet programs already?
Well, that's a tough question to answer. In fact, I mean, it's helping. The amount of money that's been dumped into HTS by the fusion community in particular has been very helpful and has started to bring the cost down a bit, but it's still prohibitively expensive, and it's really hamstringing the R&D program in magnets. On the other hand, I think that Rebco in particular has a lot of potential, and we need to learn how to build magnets out of it for accelerators. But I think in the longer term, that's a very viable option. It has the other possibility that we could operate at higher temperature, which would be a cost savings, energy savings thing as well. So, I mean, there's a lot of possibilities there. We just need to keep at it.
Okay.
Hi, so I just had a quick question. So I do know a number of young experimentalists who from like the LHC experiments who are interested in participating in accelerator R&D, and I even know at least one person who submitted a proposal. Is there any way that that people from experiment can participate in any of this? We're very good at machine learning, for instance. So.
I mean, the short answer is absolutely. But finding paths to get engaged is important. And so one of the things that the IMCC has been put together, so that's one path in. If we create something like that in the US, that'll be a path for people to come in. We have a group, there's the Advanced Accelerator Concepts group. And again, that, I mean, they would, I think, welcome people joining. That's it would be good for them to reach out and communicate and across. They haven't been focused that much on collider design, and so having that impetus would be great. There will be collaborations, and if this integrated design collider design effort is put together, there'll be a path through that. And that will also have a collaborative coordination type effort in it. And there will be paths for people to join in that way.
Oh, one more?
Hello?
It's on.
Yeah, you know, the next machine that you're likely to build, though, is the booster upgraded Fermilab, which is not yet designed, right? So the question that I have is, are you pushing P5 to, and you said that the form that that would take would depend a lot on what it's supposed to do in addition to the neutrino upgrades, 2.4 megawatts. So I imagine that one of the things that you want to ask P5 is to give you enough guidance or chart some path to enough guidance to understand how to design that machine. Is that part of your plan? Is that part of your
I think it's,
ask, or what's the or is there a plan to do that, get that input? What's the?
there are two big groups working on that. First of all, Accelerator Frontier in general is very much interested to push that agenda. And second, Fermilab specifically wants to prepare itself for P5 and very carefully consider these options and come to P5 prepared with options, evaluation of these options and how they can be done, approximate timeline, cost, and so on and so forth. Basically, the answer is yes, we want P5 to be able to say something definite on that subject.
And there'll be some kind of plan for community input on this? I mean, part of that was this meeting, but
Right.
I don't think that's.
Yeah, so Joel, I mean, I
entirely
think
converged.
the thing that what the Accelerator Frontier can provide is options and costs. But then what the physics community has to provide is, you know, what they want based on that. And then P5 has to say, well, okay, we've only got $1 billion to invest, not $3 billion.
Okay, thank you.
In fact,
Mask off.
okay,
In the middle.
someone else? Okay, okay. So in fact, in this presentation, you showed a multiple bar charts showing how much each one of them will cost, right? Are those inflation corrected? The reason is that if it is built, say today, or maybe I think, in the 10 years, or maybe about 20 years from now, it will be completely different cost. So that, whether it has been taken into account. One example is that if the main injector at Fermilab, which is built about say 20 years ago or so, costs something like nearly $300 million. If at all it is going to be built today, it will be about something like $1.5 billion. So that has to be taken into account.
Okay, I can say a few words. I was part of this discussion. So very early in the process of ITF considerations of cost, it was decided that we try to bring all the costs of past machines up to $2021. Basically, it's very explicitly said 2021 and not 2022. Because,
Which
you
is
know,
another
inflation is
10%.
already eating up our pie, right? So second, for all future projects, we estimated their approximate cost, basically cost range in $2021, but not taking into account what we call escalation, which is takes into account inflation, and contingency, which is usually a significant part of the total project cost. So we specifically emphasized it 3 times in various places along the ITF report, that's the methodology, and it's uniform across all the proposals we've seen, right? Yeah, you're absolutely correct that yes, machines in the past cost less, did cost less. Yeah.
Hey, I wanted to respond to Joel's comment, just that we had a open workshop soliciting input from the community on other physics opportunities that could have come about with the booster replacement. There was a working group chaired by Ronnie Harnack. Those contributions were written up in proceedings submitted to the snowmass process. And I gave a talk summarizing all those ideas yesterday morning. I encourage you, I'm Matt Toops, by the way, from Fermilab. I encourage you to go look at that talk or read the white paper. You know, I still think there's opportunity to put ideas on the table. And I didn't edit that white paper, but I represented it at this meeting. And in the executive summary of that white paper, you'll see that two themes bubbled to the surface. One was dark sector searches. The other was opportunities with muons, including charged lepton flavor violation and muon collider R&D. So that's the current state of the input. And I encourage people to contact Ronnie or me if you have other ideas that you'd like to put on the table.
Are we done? One more?
Yeah, thanks. Excellent talk. Really enjoyed it. Sorry, Mark Thompson, STFC. You made the point in the presentation about the need to do R&D to reduce costs of existing concepts where the numbers and power consumptions are very, very high. But costs are driven by multiple factors. This is, as you say, civil, the magnets, many, many factors. Energy consumption, similarly, it's cryo, it's power, the acceleration power, and fundamental physics limitations. So you can do a lot of R&D, but do you have any sense of what kind of delta you might get? You're not going to probably not going to turn 12 billion into 5 billion. So given that R&D, accelerator R&D is expensive activity, have you got any sense of where the right areas to prioritize are to actually make shifts that are more than just at the few percent level?
So it's also a function of what you've got in terms of timeline, right? We mentioned the one thing here with the linear collider program, and again, new RF concepts are being developed, and they'll save probably $1 billion, maybe $2 billion. So that's very significant. If you look longer term, I mean, there are ideas out there for laser-based colliders, which if you use existing technology would be very expensive. If you have advanced technology and you can develop new lasers, that could bring the cost down. Now, how far it brings down, we don't honestly know, but it would have a very significant reduction in the potential cost. Again, I don't know whether it brings it down to lower than a muon collider, for example. But that's the sort of thing that the ITF started trying to look at. And by trying to look at a project and all of its details, remember, this is just a parametric estimate that we're making. So we're not looking at any of the technological details, really. But with the ITF that way, we try to include most things and in that way come back with a more robust cost number than perhaps we had just looking at LINAC technology or something.
Okay. Oh, one,
Yeah.
the last one probably there, because it's time to wrap up.
Okay, let me go ahead. I just wanted to add a few more points to this issue of the integrated national collider R&D. I mean, Tor already gave some of the characteristics of that. I just wanted to iterate that, you bring the communities, the researchers working on different multiple collider concepts to work in a synergistic way. I mean, one example is the ILC and the CLIC communities working together, for example, on the linear collider. I mean, here we are also bringing other collider concepts so that you won't have duplication of efforts, so it would be more cost effective, as well as we think that you will also reap benefits in technology and innovation and so on. Also, it's a national R&D program, and therefore it will be coordinated and managed in such a way that it's a collaborative and cooperative effort of US national labs and universities. So this is also in answer to Isabel's question that universities, of course, can be an integral part of this.
Okay, great.
And there is going to be a session on this R&D program on Sunday, 10 to 12 in this building. So please come if you're interested in this.
And the last question.
Hi, this is Zheng Liu from University of Minnesota. I want to ask, in the past few years, has your field been stable, increasing or decreasing? And you mentioned the difficulty of international student recruitment. Can you briefly describe what's the challenge and what's your solution that you're hoping for? Thanks.
The issue is quite complicated, and Steve Lund, one of our conveners of topical group #1, probably would be the best to give answer, but it will be long, I promise you. Steve gives very detailed answer usually. So I'll connect you during the coffee break with Steve and he'll answer, okay? So thank you for your attention. So go for coffee.